So, hello everyone. Thank you for having me here. Thank you for the very kind hospitality of your country. It's a pleasure to be here. And in order to prove to my boss that I'm here also working, I would like to kindly ask you to make a cool gesture so I can take a selfie with you guys. Awesome. 3, 2, 1. Thank you so much. Thank you. So, as mentioned, I'm from Germany representing EOS. And I want to introduce you a little bit on our innovations that we have been working on. So that all is phrased under the umbrella of what we call smart processes. And the presentation that I will show you, and I want to make it also a little bit of edutaining, contains topics about Smart Fusion. I had the honor to be here last year and present already introduce Smart Fusion to you. And I want to give you updates on what happened in the background. On some recent process innovations where we feel that make a big impact on making additive just more stable and more robust and greener, and a very new product that we have launched on Formnext last year, the M300 4x1 kilowatt, that is unrivaled with regards to its productivity. So Smart Fusion, so everybody that has not heard of Smart Fusion yet, is basically addressing main problems on additive manufacturing coming from overheating. So overheating can lead to many different bad effects that could have a negative impact on your part performance. And what is the worst, of course, is a job crash. So nobody wants a job crash because then you cannot get a part that you can use for your production. What other people or the industry standard so far always was with regards to preventing overheating was to lower the build rates to take out speed from the process, to give the process time to cool down by adding minimum layer time or ghost parts where no component was really built, but the machine was just sitting there idle. It's also not ideal. You're wasting money or losing money. You can run into dimensional accuracies or microstructure and microscopical property problems, but you can also have internal stress deviations in your process, or it ultimately can lead to poor process surface quality. And as an example, something as simple as, for instance, just a cylinder that is printed on an M404, as an example, with 4 lasers, can be a very good representation of this. Because if you have very short material being molten per laser, that means you have a very short layer time. That means your part is getting hotter and hotter. And whilst it is getting hotter and hotter, the part is moving with regards to the dimension. It is shrinking. It can have shrink lines. The recoating can get very rough so that your recoater blade catches it. So a lot of things can go wrong, really, with printing one simple geometry such as that. Now going back a little, telling you what Smart Fusion really is and what it does. For instance, this geometry. If you want to print this pyramid stump on a little connection down to the base plate, what will happen is the heat from the melting agglomerates and has to travel down to that little funnel into the base plate, which acts as your heat sink. And this is something that you don't want to see in the process, because that means you have a massive overheating of your actual layer. Now, OT is an infrared camera installed in the system that can measure the gray value or the temperature that's actually happening on a layer on a pixel base. And this is actually the gray value or the temperature with the rising layers. So the higher and higher you build, the more this temperature goes up, and this is something that you typically don't want to see. So our engineers in the past have took the part and segmented into different areas and applied less and less laser power the higher they printed, in order to get a curve that is as flat as possible. And that led to the result of having a very homogeneous and smooth surface that you want to see from such a process. But nobody wants to take apart and section it in different areas and do that work manually. This is not really good. So EOS invented Smart Fusion. That is basically an automatic control system. So Smart Fusion captures the heat signature of one particular layer is calculating based on the heat map and correction table and is addressing that automatically and assigning and reducing power where it has seen in layers before overheating. And that leads to some very dramatic effects on all of the initial mentioned topics, such as dimensional accuracy, microstructure, on surface recoatability, on everything. So that is addressing all these topics at once, fully automated. Now, if you watch a process, sorry about that. The computer has a lag and I just hit the button too fast. Yes, so with the standard processing, if you switch off the process chamber light, what you really see is this afterglow of your part. If you print, for instance, this pyramid, so we are about this height, and this is really glowing, hot surface, and that is not good. That is something that you typically don't want to see in your processes, and the reason is that is a titanium process. An example: titanium melts at 1,500 degrees centigrade approximately, and with the laser, with a frozen process parameter, you're adding exactly the right amount of energy to melt the material. But if you have a funnel there where the heat is agglomerating, your building platform temperature is rising over and over again, and you're leading to overheating. So this is a bad effect. You see that also in the recoating behavior of that sample here on the right-hand side. So, sorry why that doesn't work properly, but you can really see that this surface looks very different to this surface. So here you have like edges that come up on the perimeter, and the contour is like sticking up. The recoating after spreading a new layer doesn't look very even. So this is all leading to problems. And when we take this sample and we see that in the OT images, you can clearly see that with the changing height, the thermal profile is constantly changing. And this is exactly the problem, that a lot of the applications are not really successful with standard processes. So what a lot of customers are also doing, and what EOS was trying to do in the past, is to use downskin parameters, where you start to segment your component into areas where you apply in a manual way like less and less power in areas that have seen overheating. But it's a very cumbersome, laborsome work, and it can lead to many other problems that I can address now in the next layer. You see that here also in the stacked OT images. So the infrared images or signatures really indicate you where you have this overheating problem occurring in those regions. Just not very nice. And if we take now the sample and we cut it open, from the microstructure, you can clearly see that there's something odd going on in here where this transition is happening. So that here does not look really normal. And if we start to etch the part, you can clearly see that the microstructure that you are very used from, for instance, density cubes, in areas that has seen overheating is dramatically changing. And that can lead to problems in the qualification of your part, in the quality of your part, in the reliability of your components. So how are you going to take that as a starting microstructure, do a heat treatment afterwards to make it as uniform as possible? So it's difficult. So Smart Fusion, we don't have these problems at all. So there is no segmentation in various areas where you have different microstructures and you have to tell your quality department how am I going to qualify for that. So the idea of having a smart process that controls itself is the way forward. And EOS in Smart Fusion has also the possibility to freeze those parameters. So a lot of customers are always scared, for good reason, that changing the parameters all the time can lead to quality problems. But once you have found the right recipe for your application, you can make a lock behind that and you can just rerun that component over and over again to have the same repeatable part quality and consistency. So it's about Smart Fusion. Good thing is on various applications, it really works. And we have applications here at the XAM and EOS and MCM booth where we invite you to demonstrate you that. As an example, this component, this geometry, I've printed a lot of titanium myself. No matter how you orientate this part in the process chamber, you always have some of these struts growing in weird directions that are not very favorable for recoating or recoating contact. So if you are experienced in 3D printing, you will quickly see that printing such a component is very difficult without supports. So we've reduced the supports by a dramatic amount, and it just works. No matter how we orientate it in the process chamber, it just prints fine. You don't need soft recoating for that. You can use hard recoater HSS blades, and it just prints. So it's really exciting. Another example from one of our customers, KSB, is a big impeller. I've presented that part already last year. It's a 380 millimeter diameter impeller. It weighs 35 kilograms out of Inconel 718. And printing that beast is really difficult. So you have a lot of internal supports that are almost impossible to remove. It's a closed impeller. It has huge openings, yes, but it has a lot of material and a lot of mass that can lead to deformation. If you have supports in there, the post-processing of these cavities is extremely challenging and very long time consuming. So with Smart Fusion, those were just eliminated. Also accuracy-wise, we had a significant improvement in the geometrical accuracy of the entire component. So after the printing with pre-deformation was necessary, we could achieve a tolerance of plus minus 0.2 millimeters of such a big impeller, and that is pretty much unrivaled in the industry. So a good example. Did it work on the first time? No, it did not. We needed a few iterations until this application was actually successful. And ultimately, we achieved an 80% impeller. So this 80% impeller, was 30 kilograms of Inconel. So what should we do with it? Shall we just throw it away? We thought, maybe not the best idea. Let's make the best out of it and start looking into areas of interest where the Smart Fusion parameters had to be tweaked and fine-tuned to make the part perfect. So we started to section the component into areas where we saw from the OT signal that Smart Fusion was very active and was regulating a lot, reducing the power in certain areas or increasing the power can also be done in certain areas where necessary, and have done microscopic evaluations, and we did not find anything that was suspicious at all. So even in the areas where you have very high downskin areas, you don't have increased porosity, nothing. So that means our idea and the philosophy of having a stable temperature whilst the melting is actually paying off to make a dense part, which is what you want to have in the end as a customer and application. So another application example is, for instance, this footrest from KTM and Punkel manufacturers. Typically, these footrests, they are going onto a dirt bike for motocross, and they are very highly loaded, and those parts are typically anchored one at a time down at the base plate. And this anchoring is making the post-processing very, very difficult. So KTM was only offering this to their race driver team because the individual footrests were so expensive that the little Michael Galba for his dirt bike could not afford to buy it. So it was a specialty application. And the vision was to how can we bring that into the wider range? How can we make it more price acceptable and attractive for them? And the idea was to reduce the support and the post-processing amount as much as possible and utilize the build process chamber as much as possible. And this is basically what we did. We just stacked them on top of each other, put supports in between, and there's a LinkedIn video. I'm inviting you to my social media page where you can see how I'm breaking those off with my fingers. I'm separating them. So this is unpacking metal parts like a polymer part. And it's really, really cool technology. And yes, that's how the application looks like. Another example, if you would have asked me 3-4 years ago, can we print such a cylindrical structure with 300 millimeters in diameter and 400 millimeters tall with a dome that has no support at all. And I've printed titanium a lot in my life. If you would have asked me 3 years ago, I would have said, unfortunately, it's impossible. You cannot do that. This is just not, with a cold process, not feasible. And it works. It just works. And the part is here on display. You're welcome to come over to see it, to really feel it. Seeing is believing. And the downskin in this area does not show any signs of like defects or increased porosity. It just prints fine. This is, I think, very impressive work from our engineers. And another part I also love a lot is it shall be a representation of a very small impeller that we want to have free floating, so to say, in the process chamber. And we said, okay, an impeller, we were coming to Japan. Japanese people have the stereotype to be very playful. They want to have a toy that you can play with, so please come over to our booth and get one. They're there, you can take them along. Is a blow spinner, so it's a little tabletop that you can spin and will spin around. And like typically you would print those with supports connected to the platform, but I mean, it's very fragile, it's not ideal, the part cost in the end is also not great. So the vision was to generate something like this. So instead of having a lot of them individual on one plate, just fill up the process chamber as much as you can, stack them very dense together, and make no support at all. So zero, none. And it actually worked. And here I think I have to take the cursor. How can I do that? Yeah, you can see that there's no connection. The parts themselves, they are free floating in the powder bed. We're just, removing them with the brush, and you can just see that they're falling out. So there's nothing. There's the post-processing for the removal of supports is reduced to pretty much zero. I think that's pretty cool. So our engineers did a really great job in doing that. Does it work for every application? Unfortunately not. You have still the laws of physics that you have to obey, and this is internal stress will cause that the areas will come up, and if you have too much area being printed in one layer, it will not actually work. But for some geometries, it is possible to reduce the supports really to the barest minimum. And come over to our booth and see it for yourself. Yes, so no matter which orientation, whether you print it in this orientation or just top down, both of them work just fine. Other cool technology that we've been working on is to improve, so this is now outside of Smart Fusion, the processability. So Smart Fusion taught us a lot about what is actually going on inside our systems. And there we have developed new ways of exposure that have a significant impact on the quality of your parts. So this is typically what you see, that you see a lot of sparks flying around. And the reason why we exposed here directly onto a base plate is to amplify the effect, so that you see it more clearer. They have a lot less pattern here. You have a lot less process side products that are being emitted that can influence your melting behavior. And so the effect on the parts is dramatic while using those smart processes. Those smart processes typically have a positive effect on the generation and formation of porosity inside your component. And what typically happens is customers are developers of system of hardware are trying to move porosity out of your melt zone into the outer regions or outskirts of your part. And with these smart processes, you are avoiding them to being generated. So the effect on the total porosity and the maximum defect size that you can achieve is pretty dramatic. Now, Smart Fusion also taught us that using Smart Fusion is a great thing, but it can also be a learning tool for us to develop new parameter themes that can make impossible prints really possible. And one example is a spiral coin structure with overhangs down to 10 degrees. And if you know MS1 as a material is a very difficult to operate material. So MS1 is tending very much into overheating, very much into curling up, very much into jamming with the ricotta blade. And so this part was not built with Smart Fusion, but inspired by Smart Fusion. Smart Fusion taught us to use processes of how to making this possible. And come to our booth, we can explain you how we do it. A level further is this application example that we did with a partner together, Additive Flow, on a real case application where we have used all these technologies and we've applied these technologies onto a bracket, and we have started to really tailor the microstructure to the area where the forces were the highest. So if you have a certain load on this component, the process parameters were optimized in a way that you have areas that have less requirements, so to say. They have weaker structural integrity, but they are just being exposed a lot faster. And then we have used also exposure parameters where you can let the crystals grow in a certain direction of interest. So typically customers want to have a very isotropic material, and here we did the exact opposite. We used extremely anisotropic properties. So that all leads to that you can, with the increasing design iterations, you can reduce the mass of your component, you can increase the printing time, and therefore reduce the total cost, so to say, of your application by taking advantage and use of these technologies, of smart processes. And I have to look on the time, sorry for that delay, is one system that we've just launched, the M300 with 4 times 1 kilowatt. And that system is already capable of utilizing all these technologies that I've just showed you. And that leads to an application case that is really unrivaled. In 3D printing of this machine, we can generate an output of about 1 kilogram of aluminum per hour on this machine. And how are we doing that? We are going away from this traditional having solid anchored parts on a platform with very low productive processes to extremely high productive processes, really utilizing a lot of the horsepower that we have in the systems and shooting them down into the powder bed and building them in a polymer manner. So these parts are real. They were printed and they just print fine. Just seen, thank you for the reminder of the 5 minutes that have to speed up. So in a nutshell, so how are we lowering the cost per part? So some people think you put more and more lasers into a system, your system will become faster and faster. But unfortunately, you will learn very quickly that that's just not the case. The optical components, they are amongst the most expensive ones in such a system. They are most expensive and difficult to calibrate and to have them tolerate. You will see very quickly that adding more and more lasers ultimately will flip the game. The parts will get more expensive in the end again. And there's a sweet spot, and that sweet spot is in about the range of like a 400 millimeter platform size of about 4 lasers. So putting more and more lasers onto it is not really beneficial. And you see that also, like that machine utilization is very much driving the cost per part of your application down. So this is not cost effective. You want to have the machine printing as much of the time as possible. You want to utilize as much of the building space that you have as possible to get the cost down as much as you can. And with this, I want to conclude. So EOS and our partners AMCM offer you solutions that are customized for your specific application to make your application successful. And all that together will ultimately lead that you have reliable and robust processes that are making your application successful, and that you can earn money with the using of additive manufacturing. Thank you so much for having me here. If you have any questions, just come by our booth or ask them now. I'd be happy to answer them for you. So thank you.